Hi, this video serves as an introduction to what we're going to call relative extrema and also to the first derivative test, which will help us classify the relative extrema. So on this board here I've written out the definitions of the relative maximum, relative minimum, and horizontal point of inflection. Alright, so let's assume we've got some sort of graph, which I do right here, some sort of graph of f of x. We are going to call a point on that graph a relative maximum if that point on f of x is higher than all the nearby points. So take a look at this graph and see if you can already pick out what I'm going to call the relative maximum. It needs to be a higher height than all the points around it. Not necessarily everything in the whole graph, but if you just consider a small region around that point, like the top of a hill, then you've got relative maximum. Relative minimum is going to be the opposite of that. It's going to be a point on f of x that's lower than all nearby values. So again, when you're looking at this graph, if you're trying to hunt for some of the relative minimum, consider that what you're going to call a relative minimum is the bottom of a trough. It's just the lowest point in a valley where all the points nearby it are higher than it. So that means the minimum is lower than all the nearby valleys. All right. So one more thing that we need to define is the horizontal point of inflection, sometimes abbreviated because of its long name as the HPI. And that's what I call briefly a plateau on f of x. That's a point where it kind of flattens out like a plateau, but it is neither higher than everything around it, nor is it lower than everything around it. It's just kind of a flat spot on the graph. Okay, so now let's go to this graph of f of x, and already with the definitions that I've laid out, I'd like you to try to classify each one of these points that I've labeled a through f as one of these things. So go ahead and test your understanding of it already to see if you can pick out of each of these lowercase letters, is it a relative maximum, relative minimum, or is it a horizontal point of inflection? Okay, I hope you paused the video and took a chance to test yourself on that. And now I'm going to go ahead and write what I think are the answers. Now remember, relative max is like the top of a hill. So you can see here, A, this is the top of a hill, and I'm just going to abbreviate that as max. So that's a maximum point right there. Notice how it's higher than everything around it. All right, now moving on to B, it's not higher than everything around, it's not lower, but I've marked it off, so I expect you to answer one of them. The answer must be horizontal point of inflection, and you can see that's a place where the graph is just flattens out like this, but on one side things are higher, on the other side things are lower, so it is neither higher nor lower than everything around it on both sides. Alright, however, it is a special point, and we'll figure that out why that is later. Right now, let's say it's special because it's a flat point, so that point B is an HPI. Okay, what about part C? What did you say for this one? That's a relative minimum, right? Because it's lower than everything around it. Now you could say, hold on a minute, this stuff over here is even lower than that stuff there, and that is for the keyword nearby values. You just actually technically have to define an arbitrarily small region around the point for which that definition holds. So you can see C is the bottom of a trough here, so it's a relative min, which I'll abbreviate as min. And it's lower than everything in a very small neighborhood that we've defined surrounding it. It doesn't necessarily have to be lower than the stuff over here. Okay, so that brings us to D. Now you can see the value of f of x on both C, D, and E are all negative numbers. But what kind of point is D right here? That turns out to be a relative maximum. Hopefully you knew that was maximum because it's higher, it's at the top of a hill, higher than everything around it, so it's a max. Okay, even though it's negatively valued, it can still be a max as long as it obeys top of the hill. Likewise, a minimum, even if it was up here above the graph and it was positively valued, it would be the lowest part of a trough, and so it would be called the min. So it doesn't really matter what the sign of the actual y output is, it just matters if it obeys this type of definition. Okay, so moving right along in E, that's going to be a minimum, right? That's a min there. And then last one is F, and so F, what did you think that was? Doesn't look like a max, doesn't look like a min, but it's special to me because it's a flattened out spot. So that's what I'm going to call the HPI, horizontal point of inflection. Now, a little while later, we will define what inflection is. It has to do with the value of the second derivative, so we'll go on to that later. Don't worry too much about the word inflection. Just think of the HPI as a plateau on the graph. Okay, so next, I'd like you to try to realize here on your own why I define these three special things. What do they all have in common? What do every single one of these red dots have in common? And here's a hint. The thing they all have in common has to do with the derivative. They happen to all have the same exact value of their derivative. Okay? So what do these things have in common? Try to think it out while I'm writing it on the board. All these points has to do with the derivative here. The f prime of x at all these points is what? Now, if you haven't got it yet, let's try to think about what the answer is just using the picture, because of course I haven't given you an equation, so you can't compute f prime of x. So we're going to have to think of what f prime of x represents on the graph of f of x. So do you guys remember what I'm usually drawing with the green pen, what the derivative represents on a graph of the function? It's the slope of the tangent line, right? So if we picture what the tangent line is to the graph at any point, the derivative evaluated at that point yields the slope of that tangent line. Okay, so let's picture the tangent line at each one of these red points. Let's see, at the top of this hill, looks like over here the tangent line is positive, right? When we hit the top here, the tangent line flattens out, then the tangent line becomes negative. On B, the tangent line again flattens out, then it's negative. See how that tangent line, I'm picturing it as going down, the function's decreasing. Now when I hit the bottom of this trough here, it flattens out again, and it happens to change from a negative derivative, which is associated with a decreasing function, to a positive derivative. You see how in between C and D, the function begins to increase again? Increasing functions has a positive derivative, and it does until it gets to the top of the hill. Then at the top of the hill, again it flattens out. Do you guys see the pattern? You see what I'm getting at here? So if you haven't filled in this box, fill this in, try to answer the question. What do all of these special points have in common? It's starting to look like Christmas on the board here. The derivative evaluated at each one of these points is 0. That's right. These are all horizontal tangents. A horizontal line is completely flat and it has a slope of 0. So that actually is why the word horizontal is in the HPI definition, because on that plateau the derivative is 0. Likewise, at the top of the hill, bottom of the trough, the derivative is always 0, okay? And so this is a very special property with which we are going to define what we call the critical points. Now, each of these three things that I've defined over here are called critical points. So let me give you the definition in general of how to find a critical point. And each time you find a critical point, it turns out a critical point is going to be one of three things: a relative max, a relative min, or an HPI, horizontal point of inflection. Okay? So critical points on the graph of f of x are places where, like we said, the derivative of f of x is equal to 0. However, there's one more thing that's not pictured here as an example, but also could define a critical point, or where the derivative f prime of x does not exist. Alright, now I'm going to show you examples in the examples video of other things where the derivative does not exist, but you can imagine on a function, let's say in the corner, or let's just do a little example over here. Let's say like we had a function that looks like this. Remember these piecewise functions that I would define sometimes like this and there? A. Okay, so let's call this the point A where it happens to break. First of all, does the function exist at this point? Yes, it does, because I have a filled-in bubble. There's a little bit of review. Does the derivative exist at this point? No, it doesn't, because see, the limit doesn't even exist, so there's no way, according to the limit definition, for me to define a derivative here. So here, f prime of a does not exist. Okay, final question, new for this lecture. Is A can A be categorized into one of those three things? Is it a relative max, higher than everything around it, a relative min, lower than everything around it, or is it a horizontal point of inflection where it appears as a plateau? It's probably not an HPI because it doesn't appear as a plateau. So what do you think it is? A relative maximum. That's right, it's a relative maximum because if you consider all the functional values around it, it is the very highest point around, okay? So this is an example of a relative max. But we couldn't find this one using the fact that the derivative is 0 because the derivative does not exist. Okay, so that's why we have as a definition of what are the critical points, there are places where the derivative is either equal to 0 or it does not exist. Okay, so this is going to serve as our definition of critical points, and then we can see them on the graph just like that. All right, so far so good. Now let's go into some more specific example, or actually another simple example, where I'm again going to give you a picture of a function, and what I want to do here, this is the part where I tell you what the first derivative test is I want to be able to categorize each one of these in terms of what happens to the derivative. Here you can see the derivative equals 0, but what was going on with the derivative right before the point and right after the point? Okay, so let's zoom in on something that looks like a max first, and we'll do the same thing for a min and an HPI, and we will derive what they call the first derivative test. Okay, so we're going to zoom in on a max of a function. Let's say we have a function that looks like this. Right, here's a point A at which it reaches its relative max. It's the highest thing around. Okay, now I want you to describe for me what the derivative is doing in each of these different regions that I can define. Okay, so what I'm going to do right now is make a number line where I describe the sign of the derivative of x. Now here's the original function f of x, so you can't really say that the derivative is positive because the function is above the x-axis. You have to say the derivative sign is defined by whether the function is increasing or decreasing. It's the slope of the tangent line. Okay? So as we just discussed at a relative max here, we can see that there is going to be that horizontal plateau. And so it's at this point right here, A, where f prime of A is equal to 0. Okay? So the derivative is equal to 0 right at that point. But what's going on over here where x is less than a, in this region where x is less than a, is the derivative positive or negative in this region? Hopefully you said positive, and again you're trying to picture the tangent line, and here we have a line that has a positive slope. You can see the slope of this line will be greater than 0, so this is a region where the sign of f prime is always positive. Okay, this is what we had previously described as increasing, and that's still true. This is a region where the function is increasing. This is a region where it just hit 0 right there, and it's increasing over here because the f prime is greater than 0. It's positive. Okay, now all we have left is this region over here where x is greater than a. And you can see that if we picture the tangent line here, the slope of that line is going down. So it has a negative slope. And so that's why if I was going to make this number line that describes the sign of the derivative, I would say the derivative is negative at all points here. It may have different values, like it looks like it's a little negative here, and then it gets steeper and steeper and steeper and even more negative. But if I want to make this thing, which by the way, this is called, for me, this is called the f prime sign number line. Let me write this down. The f prime sign number line. Kind of rhymes. Okay? So on this type of number line diagram here, we're just trying to describe whether the derivative is positive, that's increasing, or negative, and that's decreasing. And really, I don't want to write increasing here, because really what's going on is the function itself is what's increasing. You see how it's going up? And the derivative of the function is greater than 0 over here. Likewise, the derivative of the function is less than 0 over here, and this is what we associate with a function going down or decreasing. Okay? Alright, so now we're right about to derive or discover what they call the f prime, the first derivative test. Okay? What the first derivative test does is given information about how the derivative changed sign. Like for instance, in this case, the derivative changed from positive to negative. It will classify the extrema as one of these three different things. Now we already know this one's a max. We were zooming in on max. We can picture the max right here. But now you can see what the conclusion is for the first derivative test. If the derivative changes from positive to negative, then what type of extrema do I have? Relative extrema. Yeah, you see how we just kind of discovered that? So we're going to want to lay this out for all the different cases. And this is what's called the first derivative test. After we learned about higher order derivatives like the second derivative, we can see the second derivative test. Okay? If the derivative f prime of x changes from being positive to being negative, then the critical point is a relative maximum. See that? Now this is not something that I'm going to give you to use a reference on a test, but it is something that hopefully you feel like you kind of discovered right now on your own, because you're going to want to keep thinking about the reasoning behind this so you don't feel like you have to memorize anything, okay? So usually in a question like this, you derive a f prime sign number line, which is this number line right here that locates the critical points where the derivative is equal to 0, and then it describes the sign of the derivative on either side of that critical point. Okay, so once again right here, this is the critical point in question, and it changed from being positive, going through the number 0, and then turning into negative. There's no way to change from positive to negative without going through 0. That's why we define the critical points as the places where the f prime equals 0. Alright? So if it changes from positive to negative, then what you have is a relative maximum, and you're just going to want to picture that in your head so that you don't have to feel like you memorized it. Okay? So picture this graph. If f prime changed from positive to negative, that means I had a function that was going up, and then it changed its mind and is going down. Max. Alright? Now let's try that again with the minimum, because the next part of the first derivative test is going to say if f prime changes sign from negative to positive, then what's my conclusion going to be? The critical point is a blank. You guys probably already guessed what I'm going to fill in here, but I don't want to say it yet. What I want to do is draw a picture, and I'm going to draw everything opposite now, where I'm going to show a function that changes from negative to positive in its derivative, and we'll see what the conclusion reaches on its own. Okay, so let's see. If I can, oops, not plus, this x right there, and here's a function f of x. Let's try to draw a picture of a function that's decreasing, and then it hits some 0 bottom, and then it's increasing again. Okay, and we'll call that critical point A. That's the place where the horizontal tangent exists. Okay, which is to say that if I calculated the derivative at the point A, the answer would be 0. The slope of that tangent line, that horizontal line right there, is 0. Alright, and notice how that cuts the entire axis into two different categories. Here, if we want to draw the f prime sign number line, we're going to say f prime is of what sign over here? And if you can't remember, then just try to picture the tangent line. Looks like the function's going down, 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 and so negative, negative, negative. The derivative is less than 0 on this side of the coin. Alright, and then if we go to the other side of A here, you can see the function's going up, 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 and so that means that its derivative is positive, so the f prime's greater than 0. Please note that when I'm drawing a plus or a minus on this f prime sign number line here, I am not referring to the sign of the function. I'm referring to the sign of the derivative, because you can see this function is always positively numbered. You see it's above the x-axis the whole time. These are all positive numbers, and yet the behavior of the function is that it's decreasing here. So its derivative, slope of its tangent line will be negative. And then it's increasing over here, going back up, so the slope of its tangent line is positive. Okay, so once again, we can see that this function's decreasing when its derivative is less than 0. And then it's going back up again, increasing, and that's when its derivative is greater than 0. And I kind of think increasing is better, let's say if you're in business and this is the amount of money you're making, but depending on your application, you can conclude that either decreasing or increasing is better to you, depends on what the function is. Alright, so anyway, back to the first derivative test. If the derivative changes from negative to positive, then what kind of critical point is it? It went down and then it changed to up. So it's a minimum, okay? So that's how we remember that that's what gives us a relative minimum. Alright, great. Now we've only got one more thing, is that if it changes from positive to negative, changes from negative to positive, if it doesn't change sign at all, would be the only other thing that we can say. So if f prime of x doesn't change sign, then, and what do you think is going to be my third underlying thing? Remember, I only introduced 3 types of critical points. But again, before we fill it in, why don't we just draw it, and we can see again with the f prime sign number line how we're able to draw that conclusion. Alright, now if I'm going to say that f prime of x doesn't change sign, what I mean here is that when we do the first derivative test, we've already located a critical point at which the derivative is equal to 0, okay? It can't go from positive to negative without going through 0, nor can it go from positive to negative without going through 0. So when I'm talking about doesn't change sign, I mean, though, that I found a point where it's equal to 0, and that can happen in 2 different ways. Let's say that the thing was like this, and then it went like this, or maybe it was more like this, and then it went like this. Alright, I'm trying to draw that really well there. Alright. These are both examples of a place where, again, I've located a critical point already. And this critical point at x is equal to a has the derivative of a is equal to 0. That goes for both of these a's that I've listed here. You can see that if you drew the tangent line to either one of these a's, whether the function's increasing or decreasing, that's a horizontal place, okay? So these are both going to have f prime sign number lines. So I'd like to draw below each one of these graphs the f prime sign number line. And at the critical point A right here, f prime is equal to 0. Likewise over here, the derivative has its value is equal to 0 because we have a horizontal tangent here. Okay, but when we fill in the rest of the f prime sign number line, let's see what happens, and then you can see why I'm saying it doesn't change sign. Alright, now first of all, if x is less than a on this graph over here, what is the sign of the derivative in this region? So what's the sign of the derivative over here? The function's going down, down, down. It's decreasing. It has tangent lines with a negative slope, so it's always negative there, right? And then it hits 0. You see, it plateaued. So the derivative 0, this is the critical point. This is why we're considering it at all, is because we found a critical point and we wish to classify that critical point. But when I get to places where x is greater than a, down, 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 still going down. Dang it. So it didn't change sign at all. That means it can't be a relative max. It can't be a relative min. And what kind of point was this? When we first introduced it, that was the HPI. That was the horizontal point of inflection. And so that's what happens when you locate a critical point, but then when you analyze the f prime sign number line, it doesn't change sign. That's your HPI. Okay, so again we see it here, but the function's increasing, and then it plateaus, and then it starts increasing again. And so even though this is a critical point where the derivative hit 0, it was positive, and then it went down and it touched 0, and then it became positive again, so it didn't change sign, so you got yourself another HPI, horizontal point of inflection. Okay, so the point of this section is going to be locating critical points and then classifying them as one of these three things using what we call the first derivative test. In the next video, you're going to see me use concrete examples with specific functions.